this is a backup talk, yeah? So please don't be too, too enthusiastic about this. It is a talk that was prepared more than 1 year ago for OpenSSL webinars. I did not have time to really update all the slides. I just updated the design because the old design was like really, really boring and outdated, I would say. So we have this new, nice design of 4 slides for OpenSSL Foundation. I wanted to start with a little joke about cryptographers. So 2 cryptographers walk into the bar and nobody understands what they are talking about. So let's start with the boring part of the talk. This is our agenda. I will be talking about building OpenSSL for optimal performance. Then I will talk about optimizing EVP API usage, libSSL API usage somewhat, and also talking about how you choose the most performant and secure algorithms. Again, I have to repeat, this is 1 year old. There are probably some outdated information there, especially when we released OpenSSL 3.5 with PQC algorithms. There are definitely some changes which are not reflected there. So how do we build OpenSSL for optimal performance? Of course, you should avoid using noasm. That means on Windows you have to have installed NASM. You must avoid using D or --debug that would disable the optimizations. You might want to enable ECNIST P64 GCC 128 if performance of the bigger elliptic curves P521 and 384 on newer versions of OpenSSL, if that performance is important. This is not done by default because it requires 64-bit little endian platform. Well, actually, we could make it probably default on those platforms, but that's how it is. You might want to disable engines if you don't need them. That won't be needed with 4.0, hopefully, because they won't be there anymore. You should disable, for example, DH and DSA if you don't need them, and so on. So yeah, you can disable various unneeded features if this might help you. It will not affect speed, most likely, but it can lower the footprint of the library in memory. So that might be indirectly affect the speed, but not much. By default, we are using -03 optimization for GCC or C compiler, C-lang. You can try adding -02 or OS. They actually might provide better performance, or historically they might provide better performance for your concrete use case, platform, compiler, and so on. And last but not least, of course, you should use the latest 3.x minor version, as the performance is improved significantly from 3.0 times. And you can use the existing validated FIPS providers with the current library, and you still get most of the performance benefits anyway, because the FIPS code is not that, like the actual crypto implementations code is not that affecting the performance. This is just a little measurement of how you can make your libcrypto and libSSL smaller if you disable various things that you don't need. So this is like a configuration which disables almost everything that is obscure, basically, that you would not probably need if you need some TLS implementation that just does TLS and with RSA or CDSA. So how do we optimize EVP API usage? Of course, when we added support for providers, this added much flexibility. And there is also a larger feature set, but this comes at some costs, unfortunately. And some of the decisions were like, yeah, we need to keep the existing applications working without major changes. Unfortunately, that has really bad consequences, like we have to do lazy initialization. And that, of course, impacts other things because we need more locking, and that affects multi-threaded performance. We need to have this implicit algorithm fetching, and yeah, the fetch is not a free operation, so unfortunately. So this means that this implicit fetching will mean that there will be repeated identical fetches of algorithms, and that should be avoided if you want maximal performance. We kept support for engines and low-level methods. That I don't think that really impacts performance that much, but it raises the library footprint, maintainability, potential for bugs, and so on. So let's look at some measurements. Let's try to digest 64 bytes with SHA-256 repeatedly. So we have this simple code. We do this periodically on some different data. Yeah? So we create a context. We digest, we use this EVP SHA-256 thing, as we always did with 111 or 102 or even older versions of OpenSSL. Yeah, push the buffer to the digest and get the digest and release the context. And we do that repeatedly. This, of course, uses the so-called implicit fetch, because the EVP underscore SHA-256 is just a placeholder object that contains the name of the algorithm. And I measured these numbers on my Ryzen-based laptop with, you can see this is old 3.3.1 version. And it took now 39 microseconds for when divided by number of the loop iterations. We can make it better if we explicitly fetch the hash implementation. We don't use this implicit static object. And so we do it outside of the loop once, and then we use it inside the loop in the digest init call. What is the difference with the numbers? It takes now 0.24 microseconds per one operation, and I think this is actually very roughly equivalent to 111. There should be no regression in performance. It's 38% shorter time. We can actually optimize this a little bit more if we do this. So we, after fetching, we can also allocate the context, and we don't need to reallocate it every time. Yeah, we can reuse the context because the EVP digest init will reset the context to some clean state. So with this optimized code, it takes just now 0.2 microsecond per one operation, and it's 49% shorter than the original code. Same things can be applied to symmetric encryption. So let's say we need to encrypt 1 kilobyte of plain text with AES 256 CBC. And so we already apply these things. So we fetch the algorithm outside of the loop. We allocate the context outside of the loop. And yeah, we call encrypt init to initialize the key, IV, the cipher key, and IV inside this loop. Then we do the encryption, the final step, which, yeah, if the buffer is actually a multiple of block size, that encrypt file probably won't do anything, but it's there because for correctness of the code. So this code takes 1.16 microseconds on my laptop because I think I have the AES-NI instructions, so the AES is very fast. But we are still wasting time on something because we can reuse the preset key schedule. Yeah. So here we fetch the algorithm, allocate the context, and we can also init the context with the cipher and key if we are using the same key for, I don't know, subsequent packets or something. Then inside the loop, we need to just set the IV, yeah, and we can do that. We can split basically the call into 2 separate calls, and this will work correctly. Of course, we need to set IV, otherwise this won't be secure. Or we need to have different IV for each of these encryptions. So what's the improvement? Now 0.94 microseconds, 19% improvement, 19% shorter time. Similar things can be applied to composite algorithms, and there is one thing to consider with these algorithms. Basically, these algorithms implement internal fetches. Yeah, so you are fetching HMAC algorithm, but it internally needs to fetch the SHA-256 digest. So we can probably do something. Yeah, so this is like the normal or the basic code where we fetch the HMAC, create the context, prepare the parameter for the digest name, initialize the context with the parameters and the key, push the buffer through that computation, and get the final MAC. This takes now 0.74 microseconds if I do HMAC SHA-256 over 200 bytes. But there are, of course, those inefficiencies I was talking about, that there is like internal fetch of the SHA-256 digest. So we might do a little bit better, and this code implements that. We could create a template context where we pre-init the key and the digest into the context. And then we duplicate it inside the like periodic computation. So it's not really initialized, fetched, and initialized again and again. Of course, there is some limitation to this because the key is always the same, which in some constructs it can be actually. This takes 0.7 microseconds, and that's 5% shorter time. That's not that big improvement. Yeah. If the key is different, we could use still use the duplication trick, but it actually would not be better because context duplication overhead is larger than the internal fetch. We would not spare both fetch and internal initialization of hash context. So this does not actually help. In the next part, I would like to talk about libSSL. And mainly I focus on the client, but I have other things as well. A little bit touch the server side as well. On the client side, what I would recommend is to reuse the SSL context. Yeah, if you need to connect, if you need to create multiple connections, you should create SSL context with and preset it with the CA certificate store, and use the same SSL context with multiple client connections instead of creating it repeatedly for all connections. So there is some improvement. I'm trying to measure this, and it actually is real improvement, like in 10% or something. There is one improvement that you could use if you have a big CA certificate bundle of trusted CA certificates. Use this third directory store. Yeah, that means you should use SSL CTX load verify there instead of SSL CTX load verify file, because that like skips all the parsing of the CA certificates unless you really need them. Yeah. So these are parsed only when you actually connect to the server which certificate is changed to one of those CA certs. And only that one will be parsed. I don't have numbers for difference between using the cert directory and cert file bundle. I think it would be very depending on your concrete use case, so you would need to measure it yourself. I wanted to also touch a little the SSL session reuse on Taylor's client. If you are writing some application that uses libSSL from scratch, you will probably notice that the SSL caching is enabled by default on the server, but not on the client side, which makes sense because the libSSL does not actually know what it is connecting to. The client or the higher levels know about that, not libSSL. There is one exception. If you reuse the same SSL object for subsequent connection, there is already SSL session present in the SSL object from the previous invocation. So now let's focus more on the algorithms. This also affects servers, and actually affects servers more probably than the client. One thing that you want probably to do is to avoid using expensive key exchange algorithms. So yeah, the RSA and DH key exchanges are quite slower than EC with the X25519 and P256 curves. So how do you do that? For TLS 1.2, you can use this SSL CTX set cipher list, and that will remove support for RSA key exchange and DH key exchange. For TLS 1.3, of course, this set cipher list call won't affect it, so you need to actually explicitly set the groups that you want to use. So you can select that you want to use X25519 and P256. And whether X25519 is faster than P256 really depends on the platform. On my platform, on my laptop, X25519 is faster, but X25519 is not approved. So it also depends on your requirements if you can use it or not. How do you choose the most performant algorithms? What can help you? I would like to first start, you should never put performance over security, but what that means actually, is, so should I always use crypto with at least 256 bits security? Most likely 128 bits is good enough for me. Usually, like, there are some theoretical problems where like 256 bits might be like needed, but you should basically use the minimum security level for your requirements. Unless, for example, you have some special army clients or something which require 256 bits, that 128 should be good enough for you. Of course, always use the right algorithm for the job, because ECB is, it's fast, but almost never the right answer. So what do you do actually to measure the algorithms? You can use OpenSSL speed -EVP for encryption, for example. And OpenSSL speed command, of course, I assume that most of you know it, but it was supposed to be like a beginner's presentation, so not really for people who are already seasoned with OpenSSL APIs and command line application. I was curious, like, what is the speed of the ciphers with AED, so you can protect both confidentiality and integrity. And surprisingly, the AS128 OCB is fastest on my computer. If it did not support if it did not support the hardware, if it did not support ASNI, most likely the Chacha 20 poly 1305 would be fastest by a large margin. So you need to actually test on your concrete hardware, but that's what I would recommend. I don't even claim that the implementations of these algorithms are the fastest possible in OpenSSL. I assume there might be even better implementations, more vectorized and whatever. So this is evolving, surface. And you can, of course, use OpenSSL speed to measure not only the speed of the symmetric crypto, but also asymmetric. And of course also the digests and signatures and so on. So let's say I have a question. Which algorithm should I choose for my certificate? And if I measure RSA versus ECDSA and EDDSA on my machine, I can see that ECDSA with NIST-P curve 256 is actually really fast for signing. For verifications, the RSA is much faster, Even the 3K RSA for 128-bit security, it's faster. But what do you care about on server? On the server side, you care about the signature speed, yeah? And you don't care about verifications that will be done on client, and you don't care about that much as a server provider. So on the server side, we want to use ECDSA witness speed to 56 parameters. But in theory, RSA keys may be better for CA certs because the speed of verification is better for RSA. So actually, we should use like leaf certs, ECDSA certs, but the chain should be RSA. But that doesn't account for larger data transfer size for the intermediate CA cert chain. And data transfer is also like sucking the resources, so who knows what's actually better. It depends on the concrete use case. And EDDSA has some better security properties than ECDSA, so, and it could be probably optimized further. Yeah, that most likely could be made the similar speed as ECDSA witness speed, 256. And so most likely we would like to have both ECDSA and RSA certificate if we want to maximum compatibility. So we can set the server in a way that we prefer the ECDSA certificate if the client supports it, but we fall back to RSA certificate. We can order the ECDSA ciphers before the RSA for TLS 1.2. We do it again with setting the cipher list. I kept the KRSA, KDH from the previous example. I also remove other things that should not be needed. But it's example again. For TLS 1.3, I need to set the signature algorithm list. I can order it like this to prefer ECDSA over RSA. Actually took this huge string from Fedora crypto policies. And yeah, probably on server, you care more about server preferences. So you set this, you call this an application that you prefer server preferences. And this affects both ciphers and signature algorithms. And that's it. There are documentations for APIs and applications. They are not that bad anymore when you need reference documentation. If you need guides, yeah, there are some guides, but not that many yet. So, thank you.
Hi, Jan. Thanks a lot for interesting talk. I'm just recalling now the work of Emery Berger, I think MIT professor on profiling of C, C++, etc. And what they came up with was, or what they learned was, as far as I recall, that even like changing the order of functions in the source code affects how they end up loaded in memory. And that can affect some kind of performance later on. They even discovered that sometimes like environment variables for different users are different. This sort of squashes the space a little bit when they end up loading into memory. So I wonder if their work could actually be interesting. There's a UMass tool, stuff like that. I don't know if any of that rings a bell. I can talk to you later maybe about it. Sorry, not really a question, but I mean, if you use it, maybe you know.
This sounds really like a macro optimization thing, and I think we have bigger problems elsewhere that can much more improve the performance. I'm sorry. Like, yeah, maybe at some point when we get to like these kind of optimizations, I think we will be very, very happy when this will be the last way how to squeeze more performance. Yep.
More of a comment. I'd like to discourage over-tuning for the general audience, especially if you're setting too many very precise TLS parameters that you read somewhere. Often the advice you read is wrong, even if it comes from us sometimes. It's out of date by the time you read it. So for example, overriding the groups is probably no longer a good idea. We have sensible defaults since 3.5 and so on. So only tune when you need to.
Yeah.
If you go around, mostly you're likely to reduce the security of your deployment by disabling things that are new or not optimizing correctly.
Yeah, sure. Yeah, yeah. This is all talk that does not really reflect the hybrid post-quantum key exchange, for example, and so on. So and Victor is right. This gets outdated. So if you want to do this, you really need to know what you are doing, and you really need to follow the things. You cannot like, I fine-tuned it 5 years ago, and it should work, and I keep it that.
Also a comment, following up on Victor's comment, preferably do this with configuration files. Either OpenSSL ones or you read them, but if you're going to call the API, it should be configurable for the same reason, right? Like you may need to make changes. And then also, if you're going to be doing things with private keys, you should also load them and try to keep them loaded because of the previous presentation, two presentations ago, right? Like loading keys might actually leak information.